When you look at a huge industrial plant, what's its lifeblood? It's the piping, right? Thousands of feet of it, pushing everything from simple water to really nasty chemicals. But here's the thing, just like our own bodies, the real health of the system isn't in those big, obvious arteries. Nope, it's in every single little connection, every valve, and every support holding it all together.
Yeah, it's the piping, for sure. But, and this is a big but, if we only ever look at those long, straight runs of pipe, we are completely missing the most critical and, honestly, the most vulnerable parts of the whole setup. That's where the real story is when it comes to integrity and, keeping things safe.
Right, because real mechanical integrity, it's not just about staring at a pipe, it's about understanding the entire anatomy of this system. So today, with API574 as our trusty guide, we're going to do just that. We are going to dissect this thing piece by piece.
Okay, let's start with the absolute basics. Think of this as the skeleton of the whole system. This is what gives it all its shape and its structure. So you've got two main things here. First, the pipe itself. That's the main highway for whatever's flowing through it. And you'll always hear two key terms: NPS, or nominal pipe size, which is basically its diameter, and schedule, which tells you how thick the pipe wall is. Simple enough. But you can't build a system with just straight lines, right? That's where fittings come in. These are your elbows for turning corners, your T's for making branches, and reducers for when you need to change the pipe size. They're the joints that connect the skeleton.
All right, so we've got a pathway, we've built the roads, but how do we actually control what's moving through them? Well, that's where valves come in. Just think of them as the gates, the traffic lights, the whole control system for the piping world.
So, at the most basic level, valves really only do one of two things. They either work like a light switch, they're either all the way on or all the way off. We call that a block valve. Or they act like a dimmer switch, where you can carefully control just how much flow gets through. That's called throttling. And trust me, understanding that one difference is the key to everything else we're about to talk about.
So first up is the gate valve, and the name really tells you everything you need to know. There's literally a flat gate inside that just moves down to block the flow and then moves up to open it back up again. It's a super simple, really robust design for just stopping and starting flow.
Okay, but here's the critical thing you have to remember about gate valves. They are meant for on or off service, period. Trying to use a gate valve to throttle or regulate flow is one of the most common mistakes people make. So why is it so bad? Well, if you only open it part way, the gate just sits there and vibrates in the flow, which causes a ton of damage and erosion. And what happens next? The valve won't seal properly when you actually need it to shut off completely. So bottom line, gate valves are for blocking, not for throttling.
So if you can't use a gate valve to throttle, what do you use? Well, you use a globe valve. This one's internal design is specifically engineered for regulating flow. See, inside a globe valve, the fluid can't just go straight through. It has to take this kind of winding, S-shaped path, and it flows up through an opening, and there's a disc that you can position really precisely to control how much gets passed. That winding path is exactly what makes it perfect for throttling. It's built to handle all the pressure changes and turbulence that you get when you're regulating flow, the very things that would just tear a gate valve apart over time.
All right, next up we've got the ball valve. Now this one is all about two things: speed and getting a really positive seal. It's what we call a quarter turn valve, which just means you only have to turn the handle 90 degrees, a quarter of a circle, to go from all the way open to all the way closed.
And the magic of the ball valve is just how simple and effective it is. It uses these soft seats inside, which lets it create an incredibly tight seal. In the industry, we call this a bubble-tight shutoff. So when you absolutely, positively need to be sure that the flow has stopped and you need to do it fast, the ball valve is very often your best bet.
Okay, our last big valve type to cover is the butterfly valve. It's another one of those quarter turn designs, but instead of a ball, it just has a simple disc inside that rotates right in the middle of the flow. A great way to picture it is like the damper you'd find in a chimney flue.
Now this simple design makes butterfly valves absolutely fantastic for really big pipes and low pressure service. Think about your main water lines. And yeah, you can use them for some throttling, but it's going to be a much rougher, coarser control. You're not getting that fine tuning you'd get from a globe valve. Really, their biggest advantages are that they're simple, they're lightweight, and they're pretty cheap.
Okay, so we've got our pipes, our fittings to connect them, and our valves to control the flow. The system is basically built, but it can't just float in midair. Now we need to talk about the stuff that actually holds it all up and protects it from its own weight and all the movement it goes through.
You know, according to API574, a pipe support is way more than just a random piece of steel holding up a pipe. It actually has 4 supercritical jobs. First, it has to handle the constant stress from the sheer weight of everything. Second, it protects all your expensive equipment, pumps, vessels, you name it, from getting pulled on and damaged. Third, it has to control how the pipe moves as it gets hot and cold, expanding and contracting. And finally, its whole purpose is to minimize any potential damage while it's in service.
But what happens when the support itself causes the problem? This is the crucial twist. The very thing that's designed to protect the system can, if it's designed badly or just neglected, become the direct source of a failure. And let me tell you, this is a huge focus for any good inspector.
And this is exactly how it happens. A simple clamp can trap rainwater right up against the pipe, creating this perfect little hidden spot for corrosion to just go to town. Or the support itself can block an inspector from even seeing the pipe wall underneath it. One of the worst ones? A badly designed support on an insulated line can act like a funnel, just channeling water right down into the insulation. That leads to a nasty problem called CUI, corrosion under insulation. All of a sudden, the protector has become the attacker.
All right, let's start putting all these pieces together. Because look, knowing all the components is one thing, but knowing where they are most likely to fail, well, that's the real key to managing integrity before something goes wrong.
The API574 document is just packed with this kind of wisdom, but it pays special attention to something called small bore piping, or SBP for short. We're talking about those smaller lines, usually 2 inches in diameter or less, the ones used for drains, vents, instrument connections, that kind of stuff. And the reason they get so much attention? They are notoriously fragile.
In fact, get this. The document lists over a dozen distinct, specific ways that small bore piping can fail, just for SBP. That number alone should be a huge red flag. It tells you exactly how critical it is to pay close attention to these connections that might seem minor. They are a massive source of leaks and failures out in the field.
And here are some of the absolute biggest culprits. You've got vibration from nearby machinery causing little fatigue cracks right where they connect. They're often not supported correctly, so when the main pipe moves with temperature, they get stressed out. Then there's the human factor. People use them as a convenient step or a handrail and just snap them right off. And this last one is crucial. Sometimes they get totally missed during material checks, which means you could have the wrong metal in a really dangerous service. Every single one of these is basically a ticking time bomb.
So think about what we've just done. We've gone from the biggest pipes all the way down to the smallest connections. The big takeaway here isn't just a list of parts to memorize. It's really a new way of thinking. It's about developing an integrity mindset, where you stop seeing a system as one big thing and start seeing it as an assembly of all these individual components, each with its own job and each with its own way of failing.
And that brings us right to the final, and I think most important question. Look, it's really easy to focus on the big, obvious stuff, the giant pipes, the huge vessels. But real integrity is so often lost in the small details, right there at the margins. It's lost in that forgotten drain valve, or that pipe support that's slowly corroding away, or that little small bore line that's vibrating. So after breaking all of this down, the real question I have for you is, which small part of your system deserves a second look?